Let's take a look at the light emitting diode. The light emitting diode is found in the Semiconductors tab. Semiconductors behave differently than resistors. They don't follow the standard rules of Ohm's law, as we'll be seeing as we investigate them. So I'm going to grab a red LED here and pull it out and put it on the table. If we look on the schematic side, we see the symbol for the LED. We have a kind of an arrow shape here, and this arrow points in the direction of conventional current. So LED current must travel from left to right through the LED, otherwise the LED won't light up. And we have two little arrows here indicating that it's a diode that emits light. If we go back to semiconductors and pull out just a basic diode, we won't get the two little arrows indicating that it emits light. So that's a standard diode symbol, and that's a light emitting diode symbol. The most fundamental property of all diodes is that they only conduct current in one direction, from the anode to the cathode, from the positive lead to the negative lead. If you look at the pictorial symbol, you'll see there's a little flattening on one edge. That's the cathode, or the negative edge. I like to remember it by seeing this little straight line and thinking of this little straight line on the symbol. So this is to me like a little minus sign. Let's build a simple circuit with a battery and a push button so that we can turn the light emitting diode on and off. If I double click on this light emitting diode, I don't get a properties box. There's no particular voltage setting for the LED, and the simulation is not as strict as it is with the bulb. It's a lot harder to blow this LED up than it is in reality. In a real circuit and a 9-volt battery, you should probably put a 470 ohm resistor in front of it to limit the current so it doesn't get too hot. So I'm going to wire the positive side of the LED to the resistor to the switch, and the switch to the positive side of the battery. So we have positive flowing into the LED. Then we'll take the flat side that looks like a little minus sign, and we'll connect that to the minus side of the battery. And now if I press the button, the LED lights, and if I release it, it turns off. I've put together a couple circuits here on the schematic side to demonstrate the one-way nature of the diode. This circuit is the same as the one we built on the pictorial side. You'll see that the arrow of the LED points in the direction of conventional current, from plus to minus, and when we press the switch, the LED lights. This arrow points opposite to conventional current. It points from negative to plus, and if we close the switch, the LED will not light. Before we get into more detail about the light emitting diode, let's review what we've learned about voltage in series loads. I have two loads, R1, R2 in series. R2 is twice the size of R1. And so we can see that the voltage on R2 is twice the voltage on R1. This is true throughout the entire voltage range. If I start turning up this voltage, we'll see that this voltage here is always twice this voltage here. So this is what's known as a linear circuit. It keeps going in the same pattern in a straight line, linearly, regardless of what the supply voltage is. And that's because the resistance of these loads are fixed. This is always a 940 ohm resistor. We're going to find out with the LED that it doesn't have a fixed resistance. It changes its response as the source voltage changes, and that's an example of a nonlinear device. Semiconductors are nonlinear devices. I've replaced R2 with a light emitting diode, so we can see how the voltage splits up between a resistor and a semiconductor. Right now we have 0 volts, and I'm going to go over to the fine adjust, and I'm going to slowly increase the voltage. And you can see as the voltage is coming up, almost all of the voltage appears across the LED. The LED voltage is in millivolts, and the voltage across the resistor is in nanovolts. That's because until the LED turns on, it has an extremely high resistance, so its share of the voltage will be very large compared to the share of the resistor. So I'm going to keep doing that, and you can see that almost all of the voltage from the source appears across the LED. And this will continue more or less the same until we get up to very close to 1.4 volts. So I'm going to zoom in here so we can have a good close look at the LED. I'll back this power supply down, okay, and then keep an eye on this meter. Once we get to around 1.4, you should see the LED turn on. Okay, I'll back it off so you can see it. So there's the LED lighting up. And now as I increase the voltage, you'll see now the voltage on the resistor will start to increase, and the voltage across the LED will become almost flat. So I'll keep turning up the voltage, and you can see now this is now twice the voltage across the LED. Okay, and this is a characteristic called the diode curve. It doesn't conduct current, and its resistance stays very high until it turns on. Once it lights, it's reluctant to have its voltage get much higher than its turn-on voltage. So almost all of the voltage will appear across the resistor. What we have here is a graphic summary of the two circuits that we just looked at. When we put the resistors in series, as you increase the voltage on this power supply, the current increases proportionally. So you get a straight line of voltage increase. Turn up the dial on the power supply, you get an increase of voltage across the resistor. The diode, being a nonlinear device, a device that doesn't have a straight characteristic, was much different. We got very little current going through the LED until we reached the turn-on voltage, the 1.4 volts. Because we had very little current, we had very little voltage on the resistor in series with it. Once we reached the turn-on voltage, we got a lot more current traveling through the LED. This current caused the voltage on the series resistor to increase, but the actual voltage on the diode stays very flat. There's a small increase, 1.5, 1.6, even though we have a massive increase in current. And because we have that massive increase of current, the voltage on this dropping resistor continues to increase as we increase the source voltage. There's one very important practical consideration to this diode curve. Because a very small increase in voltage results in a very large increase in current, if we didn't put a resistor in series with the LED, we would end up with a poof situation. LED goes up in smoke. The simulation for the LED in EDISON is not as realistic as a simulation for the bulb. It will allow you to abuse the LED quite a bit before it goes up in smoke. So be aware of this when you're working with real circuits. We want to avoid the poof factor. So put the resistor in series with your LED.